So starting with the fifth unit of the 11th class, that is states of matter. We have already defined matter. Matter is anything which occupies space, possesses mass, and works when it has some extra energy. There are three states of matter. In this unit, we will consider the gaseous state and liquid state of the matter. Solid state will be taken in the 12th class. We have discussed that also. What is gaseous state of the matter? It is the homogeneous state of matter having definite mass but no definite shape and volume. Then we have the important measurable properties of gases. First is the quantity of gas. The quantity of gas is generally expressed in terms of moles, that is equal to N is equal to W by M. These are the moles. W is the weight of the gas. M is the molecular mass of the gas. So if we have particular weight of the gas and we divide that weight with molecular mass of the gas, we get number of moles of that gas. Then we have the second important measurable property, that is temperature of the gas. So it is the measure of hotness or coldness of a body, and temperature, it is measured over three scales. First is centigrade scale. It is based upon water. Here, melting point of water is taken at 0 degree centigrade. This is your boiling point of water, 100 degree centigrade. So there are 100 divisions in this scale, and we have a big division after 10 small divisions. So this is centigrade scale based upon water. Second is Fahrenheit scale. This scale is also based upon water. It starts with 32 degree Fahrenheit and ends at 212 degree Fahrenheit. There are 180 divisions in this scale. Over this scale, the melting point of the water, it is taken to be 32 degree Fahrenheit and boiling point is 212 degree Fahrenheit. So in all, 5 centigrade will be equal to 9 degree Fahrenheit. So 1 centigrade will be equal to 9.5 degree Fahrenheit, and 1 degree Fahrenheit will be equal to reverse, that will be 5.9 degree centigrade. Then we have third scale, that is called as Kelvin scale. It can measure both negative as well as positive temperature. It is based upon gases, and in this case all the centigrade temperature, they can be converted into Kelvin temperatures. So in this scale can measure both negative and positive temperatures. So this scale starts from 0 Kelvin and goes on indefinitely. Then T Kelvin is also equal to 273 plus T degree centigrade. You have centigrade temperature, you want to convert it into Kelvin, that can be changed by adding only 273 to it, will get the Kelvin temperature. So these are the three scales which are helping us to record the temperature of the gas. Then we have another measurable property of the gases, that is volume of the gas. The volume of the gas, it is generally expressed in terms of the volume of the container. It is measured in cubic meters. 1 cubic meter is equal to 10 raised to power 3 cubic decimeter, that is equal to 10 raised to power 6 cubic meter. It is also measured in milliliters. 1 ml is approximately equal to 1 cc. So these are the measurement of the important measurable properties of the gases. Then we come to the important definition. What is atmospheric pressure and what is gas pressure? Because now next property, measurable property, will be the pressure of the gas. So before measuring that, let us first define what is atmospheric pressure and what is gas pressure. So our next definition will be what is atmospheric pressure. It is the pressure exerted by the gases of atmosphere on our body, that is atmospheric pressures, or this is the force per unit area exerted by the air molecules on the different objects. This is atmospheric pressure. Then we have gas pressure. If we are having a gas sample, then gas pressure is the pressure exerted by the gas molecules on the walls of container per unit area. That will be called as the pressure of the gas. Now, measurement of the pressure of the gas. It can be measured with the help of two types of manometer. One is called as open end manometer, and other is called as closed end manometer. This is our open end manometer. This is the gas sample taken here. If gas is heated slightly, then definitely temperature of the gas increases and its pressure will also increase. And these gas molecules, they will start pushing the mercury in the other limb of this tube. Now this tube is open from upper side, then atmospheric pressure is also acting on this mercury. So in this case, what is the difference between these two levels? Let it be xmm. Then gas pressure will be equal to atmospheric pressure plus difference of these two levels, that is xmm. This is called as gas pressure. Then we have closed end manometer. If we are having closed end manometer, this is gas sample. Now this tube is joined to another U type of tube which is closed from the upper side, and this U limb has the mercury. When gas is heated in this chamber, again gas sample is heated with the help of a burner. Then gas expands and pushes the mercury in this limb. The difference in the mercury levels here. Now atmospheric forces, they are not acting because this end of the manometer tube is closed. Therefore, gas pressure will be here equal to xmm. So this is the way how we measure the gas pressure. Then we have the few properties. Question number 2, define diffusion and effusion of the gas. Now what is diffusion? Any gas leaks anywhere, diffuses in the atmosphere irrespective of its density. So diffusion, it is the phenomenon of intermixing of the gases irrespective of their densities. Whatever is their density, they will get mixed up between among themselves. This is called as diffusion. The phenomenon of intermixing of gases irrespective of their densities. Then we have second property, that is effusion. This is the diffusion of gas through a small pinhole, or we can say small orifice with some sound. It produces a sound like C sound. So the diffusion of gas through a very small hole or pinhole or through a orifice under high pressure, that is called as effusion of the gas. Then we have define real and ideal gas. This is question number 3. Define real and ideal gas. Now, what is real gas? Real gas is that gas which obeys all the gas laws and kinetic gas equation, ideal gas equation under all the conditions of temperature and pressure. But ideal gas is that gas which obeys all the gas laws and your ideal gas equation under all the condition of temperature and pressure. That is ideal gas. And this real gas obeys ideal gas equation and other laws under the you can say real gas is that gas which obeys all the gas laws and ideal gas equation under low pressure and your high temperature under high pressure and low temperature. Then we have the ideal gas, a gas which obeys all the gas laws and ideal gas equation under all the conditions of temperature and pressure. So this is ideality of the gas, which is following all types of which is behaving a normal way under all conditions. Real gas, it behaves in a normal ways only under you can say the low pressure and low temperature. Then we have the postulates of kinetic theory of gases. Now we will be discussing kinetic theory of gases, the postulates of this theory, and because of this postulate will determine the will help us to determine derive the kinetic gas equation. So before going to that theory, we must understand the difference between an ideal gas and a real gas. Ideal gas does not obey all the gas laws and ideal gas equation under all the conditions of temperature and pressure, but a real gas obeys them under all conditions. So real gas establishes an example of ideality, but real gas does not establish the example of ideality. Then we have the next question. Write postulates of kinetic theory of gases. So we have 7 postulates. Number 1, all the gases are made of extremely small molecules called as gas molecules. Second postulate, the volume of gas molecules is negligible as compared to the total volume of gas. It means large space in the gas sample is empty. This postulate is right. That third is the molecules of a gas are in continuous zigzag motion throughout the walls of container. During motion, they collide against each other. The collisions between gas molecules are perfectly elastic. Means there is no loss of energy takes place when the gas molecules collide against each other. When they collide against the walls of the container, there is no loss of energy. The pressure of the gas is due to the bombardment by gas molecules on the walls of container. There is negligible effect of gravity on the gas molecules. Then we have kinetic energy of gas molecules is directly proportional to temperature of the gas. Higher the temperature of the gas, higher will be the kinetic energy of the gas molecules. Then we have the molecules of the gas, they do not have any force of attraction between them, negligible force of attraction. Molecules of gas possess negligible force of attraction. So these are the postulates of kinetic theory of gases. Now, assuming these postulates, an equation was derived which is called as the kinetic gas equation. Now we have the next question. What is kinetic gas equation? So considering the postulates of kinetic gas equation, an equation was derived which is applicable to all the gases under different conditions. This equation is called as kinetic gas equation. In this equation, PV is equal to 1/3 mnu square. This is our kinetic gas equation. Now, modification or derivation of Boyle's law, Charles' law, and Gay-Lussac's law. From kinetic gas equation. First of all, let us derive Boyle's law. We know PV is equal to 1/3 mnu square. Multiplying and dividing on right hand side by 2. Since we know half mnu square, it is equal to kinetic energy which is proportional to temperature. Therefore, half mnu square, that will be equal to kT. Proportionality sign is removed by constant kT. So in this place we can keep P is equal to 2 by 3 kT. Now in Boyle's law, temperature is kept constant. So product of pressure and volume, this is a constant factor. Temperature is also kept constant in Boyle's law. So PV will be constant. This is our Boyle's law. So this proves Boyle's law from kinetic gas equation. Then we come to Charles' law. We'll come up to this step. First of all, PV is equal to 2 by 3 K into T. Now in Charles' law, pressure is kept constant. So bring pressure on this side 2 upon 3 into K upon P. This is kept here. This factor is constant at constant pressure. So V is proportional to T at constant pressure. This is our Charles' law. Then we have third law, that is Gay-Lussac's law. In this case again we come to the same expression 2 by 3 kT. Here volume is kept constant. So 2 by 3 K upon V, it is T. This is constant at constant volume. P is proportional to T at constant volume. So we draw all the law, that is Boyle's law, Charles' law and your Gay-Lussac's law by taking the kinetic gas equation, and then we are now discussing the different ways of calculating the root mean square velocity from this formula. So calculation of, give formula to calculate root mean square velocity. We know PV is equal to 1 upon 3 mn u square. M is mass, molecular mass of the gas molecule, n is the number of molecules. If we replace small m multiplied by n by capital M, this is total mass of the gas sample. We will get PV is equal to 1 upon 3 mu square, or 3 PV upon m, that will be under root, that will be equal to u. So root mean square velocity is the square root of the product of pressure and volume, 3 pressure and volume divided by volume, divided by mass. Since RT is equal to PV, so this can also be equal to 3 RT upon m, and mass upon volume, that is density. So this expression can also be written as 3P upon D. So these are the expressions which are used to calculate root mean square velocity of the gas sample from our kinetic gas equation. And we come to the next. What are the deviations from ideal behavior, or what were the wrong postulates in kinetic theory of gases? Correct those postulates and modify our ideal gas equation into the final gas equation. So what are the deviations? Now the next question is, what are the deviations from ideal gas behavior, or what are the faulty postulates or faults in kinetic theory of gases? So there are two wrong postulates in kinetic theory of gases. First is the volume of gas molecule is not negligible under high pressure and low temperature. So under high pressure, gas molecules come closer to each other. When molecules come closer to each other, then the volume occupied by the gas molecule, that plays very important role, and this volume has to be subtracted from the total volume of the gas. In the derivation of kinetic gas equation, we took that volume of the gas molecule is negligible, so whatever space available in the vessel, that is a merely empty space. So in this manner we cannot ignore the volume of the gas molecule, and we have to apply a correction in the ideal gas equation regarding volume of the gas molecules. It has to be considered. Then the attractive force between gas molecules is not negligible under high pressure and low temperature. So when there is a attraction between the gas molecules, definitely the pressure of the gas, it is likely to fall. Therefore, what is the fall in pressure due to generation of attractive force? We have to see, we have to introduce a correction there also. So two corrections, therefore two corrections were needed in the ideal gas equation. One is regarding volume of gas molecules. This will be introduced by factor B. Second is regarding fall in pressure of gas due to attractive force. This will be given by A. Now we have the ideal gas equation PV is equal to nRT. Now two correction, one for pressure, another for volume are to be applied. So we get P plus AN square upon V square. This will be V minus P, that will be equal to nR. Now here P is the pressure of the gas when we consider the attractive force to be 0. But attractive force is there, that will decrease the pressure. This will be small p, that is equal to A into n square. N is the number of gas molecules, A is the attractive force, V is the volume, inversely proportional to the volume of the vessel. This is the volume of the gas molecule, so this is the equation. If n is equal to 1, then P plus A upon V square, that will become equal to V minus V, that is equal to RT. So these are the two forms of van der Waal gas equation. So this modified gas equation is called as van der Waal gas equation. Now we will try to calculate the units of A and B, which have been introduced as a van der Waal constant. So you can be asked a question, give the units of van der Waal constants. This will be our question number 6. Give units of van der Waal constant A and B. Now what is A here? Small p we are considering, that is equal to an square upon v square. If we want to give the unit of A, then it will be P into V square upon n square. P is pressure in atmosphere, volume in liters, number of mole. So its unit will be A atmosphere, liter square, mole square inverse. Then we have units of B. B will be equal to what? We know that volume of the gas that decreases, small v will be equal to nv. So B will be equal to V upon N here. So in this case what we have, V is the volume in liters, this is number of moles, so it will be liter mole inverse. So we can derive the units of these two, A as well as B. Then we have few more important definitions. Now what are those definitions? Define average velocity. Define average velocity, that is represented by V. Most probable velocity, it is represented by alpha. And root mean square velocity, that is given by U. So what is average velocity? It is the average of the different velocities possessed by different gas molecules. So V will be equal to what? N1 V1 plus N2 V2 plus N3 V3 divided by N1 plus N2 total molecules. So this is your average velocity of the gas molecules. It is also calculated by 8 RT upon pi m, under root 8 RT upon pi m. It also helps us to calculate the average velocity. Then we have most probable velocity. As the name indicates, it is the velocity possessed by maximum gas molecules, that is called as most probable velocity, and it is also calculated from formula under root 2 RT upon m. Then we have the next, that is root mean square velocity. RMSV, it is given by U. It is the under root of the square root of the different velocity. It is defined as the square root of average of the squares of the different velocities possessed by different gas molecules. This is our root mean square velocities. We have also given few more methods of calculating it. They are under root 3 PV upon m, under root 3 RT upon m, under root 3 P upon D. Now what is the relationship between alpha, average velocity and U? If it is 1,